we introduce zero-error tracking for autonomous vehicles through Epsilon-Trajectory generation, and present a nonlinear control method that guarantees asymptotic convergence for vehicles with first-order non-holonomic constraints. Imagine you have a two-dimensional vehicle that cannot move orthogonal to its direction of motion. This type of vehicle is not completely controllable, so our paper extends a novel method of controlling an epsilon point in front of the vehicle that does not share the same motion limitations as the model. It can move freely about. This is referred to as epsilon tracking, and the epsilon point is completely controllable. You essentially remove the non-holonomic constraint while keeping a time-dependent controller and guaranteeing convergence of the epsilon point. Unfortunately, you also end up with a steady-state error between your reference point and the desired trajectory. See how the blue vehicle doesn't quite track the green reference trajectory? It's cutting the corners here. So to create a controller that does produce zero-error tracking, we propose the following. Tracking epsilon trajectories. We generate a trajectory especially for the leading epsilon point. That way, when it lags behind with a steady-state error, it actually ends up following the desired trajectory. How do we create it? Starting with the green reference trajectory, we exploit the fact that our system is differentially flat, and we calculate what our system states would be at every interval on the reference trajectory. Then, we find what the epsilon point would be if we were using epsilon tracking. That is the leading green X you see in the image, and it produces the orange epsilon trajectory. This is a key idea. We are using a linearization technique on the reference trajectory to create a new trajectory for our controller. What is the result? The blue car is our system, and we want to converge to the green dot by tracking the orange. We control the blue X to the orange epsilon trajectory, and we make it. The blue car has settled into the reference. Okay, let's watch that one more time. As we drive to the orange dot, we converge to the green, our original reference trajectory, and we are just using a straightforward controller on the point with a mapping to the vehicle inputs to do it. So join us as we take you through these concepts and prove convergence through a new Lyapunov candidate function and describe the motion of the vehicles in a new light. In our paper, we perform Monte Carlo simulations with varying sensor noise on different trajectories with different models and with isolated initial errors to highlight the trends of the controller. Read our paper as we show that non-holonomic constraints for wheeled vehicles can be overcome by controlling a point in front of the vehicle. To avoid the steady-state error, we generate a new trajectory for that point, and we show that it converges. Well, there you have it. The vehicle has converged. We hope to see you soon, and happy tracking.